Welcome guys to today's webinar. Thank you guys for joining. Today's educational webinar topic will be Discover the Future of eDrive Development with Simcenter 3D. I will be your host for today. My name is Mason. I'm from ATA Engineering. I am based off in the San Diego office. Very happy to be here and joined by John from Siemens, who is a subject matter expert of Simcenter 3D. He will be the one presenting the topic today. Just before we dive into the webinar, there are some housekeeping notes. So all attendees will be muted throughout the webinar. If you have any questions, please type them into the chat and we'll answer them at the end of the presentation. You will also be able to ask questions directly to John if you wanted. We'll unmute you at the end of the webinar. And this webinar will be recorded and will be available on our website and our YouTube channel. And before I hand this to John, just want to give a quick overview of ATA Engineering, who we are, and how we might be able to help support your team. So most people recognize ATA as an engineering service company. Our founders have been working together for almost 40 years, and we have vast experience providing high-value engineering services focused on test and analysis-driven design. So around 70% of our business are in aerospace and defense industry, but we also work on other industries, as you can see on top. About who we are, so we are a employee-owned small business with a full-time staff, just over 200 people. Most of them have advanced engineering degree, as you can see on the right. We have 7 regional offices across the US, and as I have mentioned before, we have years and years of experience focusing on design, analysis, and tests. So this includes everything from structural design, structural dynamics, thermal analysis, and CFD, and more. And test-wise, we are the leading independent modal test group in the US. We have lots and lots of experience flying our team to the testing article location and conducting GBT, vibration testing, yeah. All right, so aside from the engineering service business, this is how most of you joining the webinar today know about ATA. So we are a Siemens VAR, value-added reseller, who not only sells the product, but we provide software support and training. We really focus on products and solutions that helps design, analysis, and test. For example, NX is a CAD software that used for modeling. FEMAP, Star CCM, and including Simcenter 3D is mainly for simulation. And for test, we are the sole Siemens partner in the US providing Simcenter testing hardware and software. So because we sell what we use, our customer really appreciate our familiarity of the tools, and it really shows up in the hotline support function. So every time they call, they are speaking with engineers who are using the software every day and understand the problem instantly. So in addition, we teach a variety of classes, primarily dealing with simulation. For example, Nastran. If you want to find a Nastran class online, usually you find it in either San Diego or Denver, which is 2 of the ATA offices. So they're taking the registration. We are teaching the classes. All right. So I think it'll be interesting to kind of talk about ATA Engineering and Siemens history. So it all goes back to a company called SDRC, which so in the years of 2000, ATA Engineering spun off from SDRC. And we have our own company called Advanced Test and Analysis Division. So at the time, SDRC developed a tool called Ideas and later got acquired by Unigraphics and later got integrated into a well-known product called NX, which kind of started out the whole journey of ATA Engineering and Siemens. From 2007, we became the Siemens VAR, and then 2016, we became the Gold Partner status. 2018, we are the first Siemens partner doing Star CCM Plus and Heats because we love the software so much. And at 2021, we become the first Siemens partner authorized to sell and support Simcenter test and measurement hardware and software. And later on, 2023, 2024, we we're holding a lot. Our partnership became stronger, and we're holding a lot of good seminars and providing a lot of good resources. So I think this is a cool slide to kind of show the history of ATA and Siemens. All right, so lastly, I want to encourage people to visit our ATA website. It has our hotline support information, which is one of the unique advantage getting your Siemens software support from ATA. And we have a really good free resources, including past webinars, APIs, white papers that you will be able to download for free. All right, so that's for my part of introduction of ATA. I'll let John take away for his slide today. Take it away, John.
Yeah, let me share my screen. So let me see. Tell me when you can see my screen.
Yes, I can see your screen.
So first of all, is to thank our attendees for making time for this webinar, and also AT Engineering, basically for hosting these. I'm John Wanjiko. I'm based off in Montreal, and the one of the part of the product team for electromagnetics, and my specialization is actually in electromagnetics, so low frequency electromagnetics. So today we are going to talk about the multi-physics verification of an in-wheel traction motor, and we are going to use Simcenter 3D for that. And the physics or the domains that we are looking at are EMAG, safety, thermal, structure, and acoustics. And the topology that we are going to look into is the axle flux machine. But before I go on, I think it's important to thank my colleagues and also to appreciate their dedication to this project. So it has been a project that we have been going on to basically showcase how can we use our tool for that. And one thing, the good thing about Simcenter 3D is it actually allows you to leverage your global expertise wherever they are. And because it's card-based, you can basically you can be able to access the same card irrespective of the location that you are based in. It can be the same country, it can be a different country, and that's one of the things that you gain from having a card-based system. So starting off with Kangoo, I work with closely, especially on electromagnetics. Then there is our CFD cooling experts. So there's Shankar, who worked on the CCM side of it. And then there's Mike and Ranji, who worked on the Flow EFD part of the project. Then for structural integrity, we have Mark and Giancarlo. And also for acoustics, we have Bart and Sebastian. So this work has been published under 2 papers in IEEE, and they're attached there for basically for your reference. So on the agenda, you basically look at the motivation for why he drives, why are we doing this, and then why E in-wheel motor, that's the other motivation. And then we look at the key performance indicators for electromagnetic CFD, then Lotus centrifugal test. And finally, we are going to look at what I'm calling the desire, the acoustics. And I'm hoping you guys, you can stay over and see what we have in acoustics. So that's basically our agenda today. And we can start off basically with the trends. I think now it's very clear that we actually are racing towards EV affordability. Like all the OEMs are trying to get, who is, especially in the Western world, they're trying to find out how can we have a competitive vehicle that we can sell to the mass market. And not only that, there's also the competition for the market share. So, and we can see that late September, last year September, in China, Volkswagen actually dropped the price for the ID4. So it was going from 26,000 introductory price. Now it's about 20,000. And I think if you're in North America, that would be a very good deal if you, you could access an ID4 at 20,000 US. So that is in China. Then we know Tesla has been actually shaving off the prices all the way from last year, from October. They've been shaving off 1,000 here, 1,000 there. And this has not yet stopped. They're still doing it even up to today. And then in February this year, we see by BYD actually sent about 3,000 vehicles to Germany, and they acquired. They have basically gotten into these. They have actually basically gotten into this deal to be able to with the ship, they call it an Explorer, Explorer number 1, and it has a capacity for about 7,000 vehicles. So the first shipment was in this February, the 27th. And then this does not stop there. Recently, Ford CEO Jim Farley actually mentioned that Ford is trying to work out and try to find a car that actually they can produce a car that's about $25,000. And they have been working on this for the last 2 years. So it's very clear that there's a race towards an affordable vehicle. And so then there's the cost cutting in terms of who gets there first, especially in the Western world. And then the other problem that we have is today is actually the high interest rate. So that it affects not only the manufacturers, but also it affects us as consumers. So I'm going to buy an electric vehicle, I have to be able to afford it. So can I afford a $50,000 vehicle or $60,000 vehicle? So how many of us can do that? So we are very few in that. So that's why we need a very competitive in terms of price, a mass market vehicle. But also for manufacturers is like you no longer have this access to cheap credit that you can basically splash around in terms of developing your vehicles. So for traditional EMs, they have to contend that with the new entrants in the market in terms of competition, like BYD, Tesla, who do not have legacy cost. And also the good thing with this, and also the good thing with them, they're able to acquire or to accept new ways of doing things. Whereas in legacy manufacturing, we know that it's very difficult to change. Then how does this translate for us who are in the e-drive world? What is the implication of this? So it has two implications. So one, there's time and there's cost. We know that when you're developing an e-drive, what I mean an e-drive, there's an inverter, there's the charging part, there's the motor, there's the transmission. I think it takes about 4 years. So from the onset, when you say this is what we want to the time that is delivered or mounted on a vehicle, it's about 3 to 4 years. And we know that majority of over half of that time is actually testing, physical testing. And the tier ones that we have been speaking to, they say because of the rate of how fast the OEMs want to bring their cars to market, you cannot really do 4 years. You have to do it within 2 years. So that's why we believe, although we are in a period of high interest rates, competition in terms of bringing the cars to the market, we actually believe instead of less, sometimes you might think we're going to have less simulation. We actually believe we're going to have more simulations, because you cannot reproduce the 4 years that you are doing the physical test. You can't do it. It's not possible. So you need to find a way of, you still have to do those tests, but can you employ virtual verification in that? And that's why I believe we can add value into that. So how has Siemens responded that? Through the Siemens e-drive simulation offering, and this is our vision. And our goal is basically to partner with OEMs and tier one suppliers in this process of they are going through to be able to reduce not only the cost, but also the production, the cycle time from 3 to 4 years to about 2 years by offering this streamlined process. And what you basically see is that at the initial stages, when you're evaluating the design, because that's where you have the flexibility to evaluate your designs, you have the system level analysis that you can couple to in terms of Simcenter AMESIM, you can bring the vehicle in terms of maybe battery sizes, the motor size, the inverter sizes. So in the system level, you can bring the different levels that are interacting with each other. And then from there, you're able to set up the operating envelope of that motor that you have. And that's the initial stages where you bring the e-machine design. So as the e-machine design, it still has that concept. You're still not nailed it down, but you can still interact with the system level. And also if you're doing optimization, but also you can send data out in terms of losses and forces if you're looking at cooling, or if you're looking at structural analysis, or looking at acoustic performance. And then when you nail down that concept, so what I mean by that, the topology, the number of poles, the number of slots, then you can go into more into detailed analysis, fault analysis and eccentricity analysis and those kind of things. And then you also need to do a multi-domain verification process, because what is good in EMAG might not deliver in terms of thermal analysis, structural acoustic performance. And this is what Simcenter, basically, this is what Siemens vision for Simcenter e-drive actually looks like. So we are going to concentrate today basically on the detailed analysis in terms of EMAG, and also the verification in terms of the other domain. So this V-cycle basically can be lapped up with heats for design or managing the process, or you can wrap it up with Teamcenter basically to be able to track that process. So, and at the verification, what you are trying to do is basically you are trying to balance out all this interaction of the multi-attribute performance, basically. And we know this is an iterative process. What I mean by that is, imagine, and this is something that we know is going to happen. We don't know when, but I think it must happen. So with this pressure that tier ones are facing, they must be told we need to reduce the cost of the drive by this amount of money. So the highest that you see is going to be how can I reduce the cost of materials? So can I make a smaller device? And the other one, can I swap materials with a cheaper one? Or in terms of magnets, can I actually have a topology that does not use magnets completely? So that is going to come. That's a vertical requirement where the the management says you have to reduce this by this amount of by this factor. Then after that, so if you are the EMAG structure, basically it sets up, it's a small portion, but it sets up the rest of the process. And you can see that if I switch my machine from a PA machine that is using magnets to a machine that does not use magnets to basically an induction machine or a switched reluctance machine, that has other implications in terms of noise, in terms of cooling, because there's a induction machine, I need to cool the rotor. Use the switch reluctance machine, I need to deal with those vibrations and integrity issues. So you see that this is an integral or is an iterative process where the decision of one physics might actually affect the rest. And that's why you see there's the higher level, vertical requirement, cost, material, weight reduction, and then there's the horizontal, how the physics interact with each other. And one of the contributing factors is because you want to reduce the mass as much as possible, it actually affects the rest of the masses, the electromagnetic mass, or the saturation of your steels, the cooling, you're reducing the mass, or the transient, the structural integrity, vibrations, and all that kind of stuff, by just reducing the mass, physical mass, basically. So, and then the only thing that you see in all these is all these are separate. You have different mesh models, simulation models, and the only source of truth for all these workflow is just the design card. And the question is, how can we use that design card? And that's where Simcenter 3D becomes very important. So in a normal conventional single physics workflow, where me as an EMAG, I sit on my own streamlined process, or an acoustic person or a thermal person, this is basically what you are going to get. You're going to get the card. So the card design team is going to come up with a card. I'm going to import it, uh, or I'm going to talk to them nicely. They clean it for me. If it's dirty, I have to return it. If it was produced for card design, it's not the same for CAE analysis. And then I will do the pre-post. This is the setup, solve, and do the analysis. That's what you do the normal process. Now, if I adopt Simcenter 3D, which is card-based and based on the NX, then if I have an X on the over there, I just consume that card as is because it's NX based. Then because I'm cleaning it and NX keeps, or SimCenter 3D keeps the history, it will not forget what I'm doing over there. And I've already immediately this import step, so that is already gone. Then I do my pre-post, I solve, I do my analysis, already have gained some step by basically reducing this import step, because SimCenter 3D allows me to grab what I need for my analysis. So for EMAG, I just grab the EMAG bodies. If for CFD, I will add my CFD cooling on top of that. If I'm doing acoustics, I'm gonna add my acoustic pieces, or if I need to add other things. So that's what it allows you to do. Then, because you said it's an iterative process, if I change things, then I don't have to do this step again, because it's remembering what I did, and that's why we are saving time. That's why we are saying SimCenter really gives you an efficient verification workflow by actually eliminating some non-productive tasks. So the benefits is you only spend the effort once in setting up the process. And if that process is associative, anything that you do on the card, then you should propagate immediately. And then you want to spend effort and time basically to recreate the card, update, then solve, and then do the analysis. And we believe this is what Simcenter 3D adds to the verification process. Then this is the process that we are going to try to use to showcase using an in-wheel motor. And then we ask yourself, why an in-wheel motor? So we need to make a case for that. And this is the simplest case that you can ever have. Is basically, if you look at this skateboard, basically an all-wheel drive skateboard, you have the front part of the drive, and then the back part of the drive. So if you are to move this drive, basically you propagate them to the wheels, this is what you end up. And it's basically, you can see that you have more room for cargo and passengers. The problem with this is you shift all that complexity to the wheel well. So that's what you get. So you get more volume, but you have to, there's a price to pay. And the price is basically the handling and suspension system because of the sprung mass. Protecting these basically from the environment, water, dust, sand, all that, ice. Then complexity, bringing all the power. You're bringing the power, the coolant, the controls into the wheel, and it's each wheel. And then you also, because you only stuck with this small space, that's all where all your torque has to come from. There's no other place to produce that torque. And if you ask us to be a two-wheel drive is not even a four-wheel drive, then it's even more worse, because the larger the vehicle, then the more that wheel at that local level you need to produce that power density. And that's the interest for our discussion today. So then when you get to a new wheel motor, then you have to ask yourself, which type of topology do I choose? So we know that outer rotor machines gives you more torque than inner rotor machines. So, and it can be radial flux or axial flux. At a simple, at a local level or at a very low level, you can basically look at it and say, you know what, for this topology, I have one flux producing region. I only have one air gap. So we call that an air gap. And what you see, the gray is the rotor, I don't know what color, the orange is the stator, and we say is an outer rotor gives you more torque than when it's in a rotor, like the radius, because torque is force times distance. So the farther you are away from the center, the higher the torque. That's why you are going for an outer rotor machine. So the axial flux has two torque producing regions, and actually you can even add a third one over there. But the question is, immediately you do these, it actually has implications on your development process. So we know that radio flux machines process or development process is very well standardized. And 2D, especially for electromagnetics, 2D is good enough until maybe you go to verification where you can bring in the 3D. But when you go to this kind of machine, axial flux, transverse flux machine, or another machine that you can put, because you can actually put another cap over there, and then you have a third air gap. Basically, you have to work, you have to use 3D analysis. That has implications, because if you are doing optimization, the time it takes to solve a 2D model versus a 3D model is maybe twice orders of magnitude or one order of magnitude higher, depending on what you are solving for. Then the cooling also. How do you cool a sandwich? Because that's the stator, and you know the stator has a height. So how are you going to cool that? Then the other part that you have to ask yourself, because these magnets in a radio flux, they are buried, or you see like the rotor is outside. So in terms of holding them structurally, you are containing them. So it's easier to hold them over there. Here, they are radially. So how are you going to hold them? And then how do you analyze vibroacoustics, rotor, stator, or both? So so you see from an outset, by just selecting the topology, the electromagnetic topology, it actually has implications in the subsequent analysis that you're going to do. And then we threw in some more spanners into the works. Basically, we said a number topology is held like that. So you have one knot over there, you have a bearing and a bearing over there. Then we are like, you know what, let's remove this bearing and put it over there and move these utilities over there. So basically, move this bearing over there. Let's use this port to provide the utilities. That's the coolant, the controls, and the power. So the goal is to maximize the power density, because now you have this extra delta that you can, because this fixed volume is fixed, you can't do away. It's the wheel well, you can't go higher than that. So, but you can actually play around with these. But it has so in electromagnetically, this is extremely efficient because I'm gaining a delta over there in terms of diameter. I'm getting higher power density. But structurally, how do I suspend this overhang? And then what's the implication of me holding the stator from the inner radius in terms of thermal? Because remember, I'm using a smaller surface area because I'm using a smaller diameter to extract the heat, and I'm using it to hold it structurally. And so what does it what's the implication for that in terms of structure or in terms of acoustics? And what's the implication of structure in terms of this overhang? So those are the things that basically are going to come into play. So we didn't have to look far for a motor, a candidate design. So we reverse engineered this motor, and that's the reference. And the most important part to look at is the torque. The torque demand, the rating was about 350 Newton meters at this 75 amps. And then the continuous torque about 150 at 120. But the most interesting part is the current density. So it's 14 amps per millimeter square. So, and if you read down there, basically for the rule of thumb is below 5 amps, use natural cooling. Above, between 5 and 10, fan cooled. Above 10 amps, you're doing liquid cooling. So depending on, so that's how you either, when you shrink a machine, because now you have, remember, you're delivering the same mechanical, electromechanically, you have to deliver the same load, the same performance, whether you are shrinking or expanding. So the more smaller you make the device, the higher this guy is gonna go, the current density basically. So in terms of materials, we are using UH because it has very high temperature tolerance. So you have to make those decisions as you go. So here there's no cost implications. We do not consider the cost. Then we assume the SMC materials for the rotor core, for the stator core, the coils, Kapton for the insulation, and then aluminum because it's lighter, and this is aluminum that can be used for like the one that used for aluminum limbs. Then we are like, this can be an affordable material, and then use it for the outer part of the cylinder for the stator because it's less subjected to the flux, because the flux is going to be axial, and then use it also for holding together the rotor assembly. And then peak because it has very high temperature tolerance, and we can use it basically to hold the stator structure together. So these are the material properties, but the most important thing here is to look at what is highlighted in red. Basically, it tells you the magnetic materials, the one that are used for energy conversion, has very poor tensile strength. So you can see this is 80, 65, and 69 for the insulator, except copper, which is actually higher. And then they have very poor thermoconductivity, except copper. So this is very interesting for the rotor side because that's the one that is rotating. That's the one that is going to be subjected to braking, like when you brake, like reducing speed, changing speed. And you can see basically you have to protect these magnetic materials basically. And then the other thing that you just noticed, the maximum operating temperature, as I said before, because that depends on it's going to affect your cooling. So that's just material selection without even going to the design and how actually the design operator responds. Then we dive into the electromagnetic APIs. And what you like to do basically, or what the normal process is, you just do the motor characterization. So the first thing that you are going to do if it's a PM machine like this one is you're going to extract the static torque curve, and then what you call the maximum torque per ampere. How much torque can I get for a unit of ampere? And then you also have to do it under the DC bus limited. So that is just electromagnetic efficiency. We are not looking at thermal. We're just looking at how much, if this is a structure that I have, how much torque can this structure give me? Because at the end of the day, that's what you're looking for. Then, because of thermal issues, you have to have as accurate as possible the electromagnetic power losses. And then you also have to look at, so that is detailed analysis. How does this thing perform under different demagnetization conditions? But for us, in this case, we are looking at the extreme demagnetization condition and then under fault analysis. So we start off with static torque curve, which is basically what we usually do here is because the motor can be said to have two feeds, the stator feed and the rotor feed. So here what we usually do is we align the stator feed in one of the axes of the faces, or let's assume it's face A, it is an ABC system, three-phase system. So we fix the rotor with face A, and then what we usually do is we rotate the rotor field, which is basically the magnetic field in the rotor. And then we're going to see how they align and where we get the maximum torque. And usually do it for a different set of currents. So for us to translate this back to what we are looking for, our target, 150 Newton meter to 120 and 350, I transformed, because usually you inject a DC current, I transformed it back to RMS. So here there's no rotation, it's static. That's why I call it a static torque curve. And you can see the structure is very good because you are getting, we can get what we are, but this is very ideal, and this is what you actually use for controls. So, but because you're going to use direct cooling, we need to introduce some gaps between the coils for the cooling channels. We explain what is direct cooling later. We remove some materials for the SMC, and that's what you see the impact is. Basically, I'm reducing some materials, so it actually affects my torque capability. But in terms of torque, if we can cool this thing, we can actually go very high in terms of torque capability. So that's the good thing. If you can get rid of heat in a machine, you can go as much as high. That's what this curve is telling us before you start flattening. So then from this curve, usually you get the torque speed curve, but it's because the 3D machine, and that's what I was saying, the implication of 3D is I cannot show for all these operating points. So what I did is basically I select a point where under the DC bus limit, because the DC bus can only give me this much. Then under there, then I get the maximum, which is the speed that I can get the peak torque. And then I know below that and below, like if you look at this triangle, basically there you can be able to get this peak torque. So this still electromagnetic, it's not thermal issue, structure or whatever considered. Then what you see, these envelopes, the rated and the peak, those are basically derived from analytic expressions. Then below that, I use the rated current basically to derive so these operating points. So I have 1, 2, 3, 4, 5, 6. So I don't have to generate that because this is basically telling me I can basically extrapolate to 0, because if I can generate this, I have enough voltage basically to be able to generate that peak torque. So so basically here what we are saying is you can't because you're using 3D. The assumption is you're going to need very huge starting torques during the startup of the vehicle. And then at higher speeds, you might not need that high torque. That's why it makes sense to look at peak torque at these low levels and then look at continuous or rated torque at high speed where you just need to overcome the drag from the vehicle. But at these low levels, you need to overcome the inertial component. Then after we move from that characterization, then you go to your magnet and say, how do I segment my magnet to reduce the magnet losses? So what we have done in our solver, what we do in my magnet solver is we have something that we call the path critical insulation. Usually in some solvers, you have to basically introduce a gap to basically model the groove or what is between the insulation between. But what we have is a reduced order model, basically we call it perfect critical insulation that prevents the current from leaking from one body to another, although they're in touch. So that's what we are using. So we are not physically meshing the gaps between the pieces. So another way of saving time is you don't go each model. You have segments like you'd have how many? You'd have like 5 types of model. So you can choose one model and then you play around with it. So you have a magnet that is non-segmented, 8 segments, and that's what we have done over here. So, and then you choose the speed, especially the maximum operating speed is the most important. So the maximum operating speed is the most important. And then from there, you can see the magnet performance, the segment performance. So I chose the rated speed or 2000 and then the 7,500 RPM, and you can see the losses. So we can see that what was unique, what was good with these is you can see the 4-pole segment with a pole arc, with a pole pitch. If you call this a pole pitch, is actually performing better, very close to the eight segments. And the good thing with this is then you have less segments to assemble in terms of manufacturability. So this way you can be able to choose a method that actually gives you less cost for manufacturing or assembly. So that is trying to reduce the cost of one, assembling magnets, bringing them together, and also basically suppressing your eddy current losses. Then one of the things that you have to do is actually demagnetization analysis. So there are different ways you can look at it. So there is rated, you can do overload conditions when you overload your machine, or you can initiate a fault. And then what you usually do is you set it at 2 temperatures. So in your solver, you can set at 2 operating temperatures. So in this case, we considered ideal 20 degrees and 120 degrees. So the way you usually do it is you have a no load, you do one cycle. So this is phase A, one, you do no load, so the machine is not loaded. And then the second cycle, you load it with an overload. In this case, we are using a demagnetizing field, and then you unload the machine. That's what you see. So you have 3 sides, and then you unload the machine, and then you compare the back EMFs before and after going through the fault. So in this case, what the fault that we have initiated is actually when we say, I have my magnetic field and I have my stator field. If I make my stator field to oppose my magnetic field, so that's what you say IS is equal to ID. ID is responsible for the flux, that is flux that opposes the magnet or the magnetic flux from the stator. You can use this ID to do that. That's what the controller does in the inverter. And IQ is the torque producing component. So you can split it into a phase of ID and IQ. So basically here I'm making all the flux, all the field from the stator to oppose all the field from the rotor. And this is what you see in this between 10 and 23 milliseconds. So in the first phase, for the 20 degrees, you can see already between the two, because we know that magnets are temperature dependent. I've already lost some magnetism, about 11%. Then I go through the short circuit. I have a positive. I'll explain where this positive is coming from, because you'll be like, why the heck is that thing over there? Then you can see between the two is about 52%. You can also consider it vertically, so 10 and 11, and you can say then 10 and 11, this is, you can call it mesh error or noise, 11 and 10. Basically it recovers. You can say that at low temperatures, this machine will recover. At high temperatures, you can see this is 9 and 5. So it's already lost 50% of its magnetization. So basically it's telling you, if your machine goes through this fault, the way it is at 120 degrees, basically you have lost 52. And because they are hard magnets, you cannot recover that. 50% of it is gone. Basically 50% of your torque capability is gone. So that's what the inverter is supposed to be protecting the machine against. So this 17% of explain what it means. Basically what we do is this, we call it a current driven case, where we say we are imposing current on the windings, and then the solver responds on the same winding, you're gonna get a voltage. So that's like is an inverse problem basically. So what you get is basically it tells you if I was to drive this current, this is how much voltage I will need. Because you have gone through demagnetization, that's why you have a very high voltage than on this case where you have not gone through demagnetization, and that's why it's high. So you can look at it and say, if I go through demagnetization and I want to produce a certain torque, I actually need more voltage to do that. And that means because my DC, my battery is limited, I cannot deliver that. So basically that's what that positive over there means. Then, as I said before, for losses, you really need to account for to make them as accurate as possible. And then the same case, we are going to save time as much as possible because it's a 3D machine. So it's a divide and conquer mechanism. So we use the same PIE, perfect reticle insulation. We basically make these links or they look like conductors. We make them the same, we separate them, but then we add the perfect reticle insulation so they don't conduct with respect to each other. And then the reason is rectangular windings are very good because of very high slot field factor, the very the amount of copper in the slot, and also they distribute the heat evenly. So that's the one good thing about rectangular than random winding. But they also have a huge problem. They are subject to very high AC losses. And then the other problem is very hard to wind them. If you turn these winding, like you make them thin and then you lap them on top of each other, it's very difficult to reproduce that kind of winding. So then what we did, or what I did, is I landed between 900 RPM all the way to the maximum speed. And then what we have done is I compared the loss at the mid section of the machine to the outermost section, which is close to the air gap, and that's what you see in this car for different speed. So what you see that for very low speeds, actually you can tolerate that even at 200, 2000 RPM, you are still safe even there. But what it tells you at maximum speed, this outermost turn is carrying 9 times what the turn in the middle is carrying in terms of losses. That's why we have this loss ratio. So the removal of heat at the 7500 RPM or the coolant failing, your coolant failing at 7500 RPM has very huge implications than if your coolant failed at 900 RPM because of that. And also if you are to mount your sensors for controls, like for protecting your machine, you will not mount it so on the middle of the machine. You really mount it now close to the top most winding because that's the one that has the highest losses. So this also gives you the feel of how to use digital twin. That's a good example of how localizing sensors. Then from the loss analysis, so we have our magnetic loss analysis, we have our losses for the for one tooth, and then basically from that we can basically derive now the loss distribution over the speed. And this is very important. So as I said before, we made the assumption that I need the peak demands at the initial stages when I'm accelerating the vehicle. And then at the higher speed range, I'm maintaining, or my cruising, I'm just maintaining my speed. And that's what you see over there. So here is the peak demand, and that's the maximum speed. The good thing, as you can check from the color bars, is like the winding losses are very high. And then the stator, core, the rotor yoke, and the magnet increase with speed, as you can see in this per unit system. And this is referring to the base speed at 2000 for the rated condition. So that's the peak, that's why they're high, and that's why there's that unsymmetric in terms of rotor yoke. But the others, you can see they have a projection that they are following, they're increasing with speed. So this tells you, if you look at rotor yoke and magnet, basically it tells you, if I'm looking at the loss transfer, if I'm designing the cooling system for the rotor, I need to go to the maximum speed. If I'm designing for the stator, I need to go to this to the peak torque operating point. And that is what we have now. That's the conclusion that you get from this slide, is that for the stator cooling analysis, I need to consider the peak torque, or where I'm required to generate the peak torque, because that's the maximum that I can. And then for the rotor, the maximum speed is the most important, because I'm getting this rotor passing frequency that are influencing the losses on the rotor side. So that's what it is. So it also tells us one additional thing, this slide, you don't have to do your thermal analysis on the whole operating speed region of your machine. So you can select 2 operating points that can be able to represent the stator cooling analysis and the rotor cooling analysis. Then after that, we have been able to choose where we're going to do our CFD thermal analysis. We've been able to characterize our machine in terms of the envelope, the magnet, and also the AC losses, and we have selected, oh, we know where we're going to do. Then how do we do our structural analysis, especially uh, for acoustics or for structural analysis? And one of the things that you have to check is the centricity, and also which condition gives you the worst case scenario in terms of electromagnetic forces. So for axial flux machine, the worst thing that you have to deal with is the axial force. It's very difficult to deal with because the machine is basically attracted to the rotor in the axial direction and wants to dislodge the magnet. Basically, maintaining that air gap is a challenge. Then some analysis showed that the three-phase short circuit gives you the worst in terms of forces. It actually gives you the worst. It's the worst case. And then we're able to do about 40% of air gap centricity. So, and then so how we did it is basically you do for the so we have two eccentricity problems, axial and dynamic. Axial is like because I have two air gaps, is I shift the state at one side, so one gap is longer and the other one is shorter. And the axial centricity has a huge implication compared to conical. What you are seeing here, in these is conical dynamic, because conical dynamic is basically wheeling around the stator, but because of averaging, each piece of the rotor is seeing the same thing over a 360-degree cycle. So yeah, it has those loading. You can call it dynamic loading on there. It's not seeing the same thing. Whereas axial, in one side the gap is smaller, the other side is wider. But on the global scale of things, what you see is this. So if you look at the orange one, this we consider only for the rotor. The other one is reflected on the other side, and the balance is what you get. So this is rotor number one, but rotor number two will be the same, but on the other opposite side. But for axial centricity, what you get because of that unbalance between the two, you get this preloading on the stator side. So you have this DC, you can call it a DC offset, basically that is seen by the stator. And then this is one of the rotor. And then after that, I apply a short circuit that sticks about mid-seconds. And then you have this field that's going down, and then the forces are going up, peaking over there, and then decreasing over there. Then for conical is very interesting. And actually, if you mount a sensor on the shaft, you will never see it, because you can see in an ideal case, that's what it does, because it's averaging all those. So if you have a torque sensor, it won't see conical. Actually, it might see axial, but it might not see conical, because it's averaging all the effects. And that's why you see for the stator that is under conical, the value is 0 because they are balancing out eventually. And then you can see that so there's no shift. And then when I apply a short, it goes up. So I have to do this to make sure I do a whole cycle. And then after that, it decreases. So at this larger scale of things, if you're looking at this from the outside, you'll be like, then where should I do my analysis? So in this case, we said, you know what we're gonna do, because the axial has this shift, is increasing on one side of the rotor and decreasing it on the other, and that's why you get this shift on the stator. Then locally, it means things are not. If you go to the local level, the forces are not the same. Then they are like pieces of magnets on pieces of the stator that are actually more loaded than the others. So we went ahead and looked at the axial centricity. And if you look at these, it's very weird. Here, in my mind, I'm like, this is where I'm going to look for the maximum forces. But what I realized was this. If you look at here, you have 4.8 going to 6. Maybe you're adding 2 at the worst case scenario. Look at this shift from here all the way to here. Normal operation is about, they are close to 5. Here, you are reducing about 4 kilonewtons. So that's where we went ahead and said, let's go to the individual magnet and see what is happening in the individual, look at the force magnitude. And that's what you see. There's these shifts that you see in the force magnitude. And then you are able to identify and say, instead of, initially you would have said, I would do my analysis over there, but then you're going to do it over there. So if you're doing a static analysis to check the yielding, that's what basically we did, to check where at the local level, because that's where the yielding is happening at the local level, not this is global, this is local. Then that's why you need to go identify which part is it that is having the maximum, basically, the maximum force in terms of loading. So in terms of electromagnetic, basically characterizing the operating envelope, looking at the magnetization, you can be able to look at the fault and the highest operating temperature. And then it also gives you a feel of insufficient electromagnet cooling, because you're gonna know which temperatures can I tolerate for the magnetization. Then you need, for CFD thermal, you need to get your losses correctly. And then we saw that you can actually choose 2 operating points. For structural analysis, you need to find a point where you have the worst case in terms of forces that are being produced. And then at the rock level, you need to find a place where so the goal is to avoid using the transient for static for structural analysis and use the static. So basically, if you can identify the point where you have the highest forces. So then after that, we navigate to CFD Ramo. And CFD Ramo was also interesting. But the goal here, the greater goals is like, can you maintain operation at rated conditions, accelerating torque, and cruising speeds? The good thing with the interesting part with CFD Ramo is we know that you have to maintain the driving behavior, the driving feel, irrespective of how the driver drives, where they drive, the drive cycle, or where they live, the ambient temperature. Whether you're in the Arabian desert, whether you're living in Alaska, you still need to drive your vehicle. And you as an engineer, what you have is actually the only thing that you have control is the cooling structure, the type of coolant, the flow rate, and the cooling circuit. That is, it has to regulate the inlet coolant temperature, because after going through this cycle, you can be able to tell how much can you tolerate. So use the Freedom Car guidelines to guide us on how to set up the solver. And then the analysis is basically choosing the cooling channels, like which kind of channels, especially for the state, do we select. So we use the rated current at 2000. And then as we identify 2 operating points, the cooling performance at peak current, and then the rotor cooling performance at the maximum speed. Then for the EMAG parameters to reduce the computation effort or the transfer of data between the EMAG to the CFD, we use volumetric losses per body. And then we assume the isotropic thermal conductivity. And then the target is, can we go less than 120 degrees? And then for the magnets, we need something that cannot demagnetize our magnet by less than 10%, because you need to have, so that's on the rotor cooling side. So in CFD, you have 2 solvers, and there is a steady flow that is well suited for stator, because you have very low fluctuations, and it solves actually faster. Even for a normal reflux, if you have channels, it can give you about an hour. So that is something that you can do. Then we have the transient solver that is a fit for rotor, because it has to capture the rotor interaction effects between the stator and the rotor, the fanning effect, and this is computationally expensive. So why then, how did we come up with the cooling design? Basically, because of the size of the machine and the amount of torque that is supposed, especially the peak torque that is supposed to produce. So if you just look at the power density, the current densities alone, it's already going to the liquid cooling. And then we thought, what if we trapped the heat, or we extracted the heat at the source? That is, we know the heat is coming from the coil. So if you actually can get the heat out from the coils, then it will not spread to the rest of the machine. And then that way we can be able to tolerate very high current loadings. And that's what the direct cooling tries to do, is to go at the rocker level and try to extract the heat with, like, the same way you do in a transformer, and then preventing it from spreading to the rest of the motor. The problem with that is you really have to hold that structure. So the structural analysis of that the structure becomes important. The good thing is an active flux is amenable to direct cooling. One, because the teeth are modular, as you can see. You just need to introduce that duct in between, and then see the impact of duct on the electromagnetic performance. And then you can be able, so as long as you can be able to hold these coils in a suspended in a fluid, then you can be able to actually apply direct cooling. So we had 3 cases that we considered: single channel type 1, type 2, and double channel. And then the single channel type 1, the fluid is coming in, circulating circumferentially, and all in each. You can see it's doing a zigzag, and this is the same thing that we do in a transformer in a zigzag form, and then out. And these are the flow velocities. And then here the fluid is splitting into 2, following the same zigzag pattern, the same way, following the zigzag pattern, and then assembling at the bottom. And then here a double channel is basically a single channel type 1, but with counterflow. So in one is rotating clockwise, and the other one is rotating counterclockwise. So this is the performance. So it's a comparative analysis. It's not about the temperature, but comparative analysis. And you can see that the fluid is going from the bottom and then being assembled at the back, at the top. You can see that the temperature distribution and also the hotspot is higher compared to the rest of the single channel type 1 and the double channel. What you also see, so if you change the scale, you see that the single channel, because the fluid is basically recirculating like that, the problem you get is this non-uniform temperature distribution, and that's what you don't want in terms of because of thermal aging. So you want to distribute the temperature as much as possible. So those are some of the decisions that you can make. So that's what you see here is what this double channel does. One circuit goes clockwise, the other one is counterclockwise. And this way you are able to even out the heat distribution. So, and then for comparative analysis, we use the maximum limit that we had. And then we can see then we threw in engine oil to see what's the impact. But you can see this one gave us the lowest hotspot followed by that. And then engine oil, because the capacity is not as good as glycol, but we just do it in there to see how does it perform with respect to the other. So from that point, we assume ethylene glycol. Then at the peak loading, so it was very clear we cannot, this is not going to give us 120. So we reduced the inlet temperature to 25 degrees. We ended up at 125 degrees. So they still the 5 degrees, basically saying that you really need to, your cooling circuit has to push it down. Also, the other implication it actually means is you cannot deliver this 375 amps peak current at 900 RPM. You need basically to reduce it and see how much torque you can produce. So you can see that electromagnetically, you can produce very high torques, but thermally, can you be able to sustain those torques? That's basically the question. So for the rotor side, we did the same thing, but for the rotor now you have the unsteady over for 3 mechanical revolutions. And what you see, the interesting part that you see is the stator is very cool at rated current. So meaning we can sustain the continuous current demand of 120. But then when you look at the rotor side, because you see the rotor core is very cool. And then on the magnet side, this 120, the magnets are hot. So the magnets are running hot. And what you see, the fluctuation is the gap between the two magnets. But this is before we added the mechanical structures for holding this structure, for holding the rotor side. So this has not been redone to consider those effects. So this is when you assume, let's assume I only use the steady state. So but there's no rotation. You can see on the rotor side, you've estimated is extremely hot. And then with rotation, because you are taking the fan effects into account, basically you can see the hot spots. Basically the temperature is a bit is lower. And then here you have very huge temperatures. So in terms of time, the steady, as I said before, you can use it. I think, and even an email engineer can train himself to use them. The turnaround time is very good, from 25 minutes to about an hour. But then you can see that with rotation, the best that we could get with 40 cores about 8.5 hours. And then if you go for the mechanical revolution, 16 cores about 17.5 hours. So for 3 mechanical revolutions. So in conclusion, basically then you can say steady state solver is, you can use it especially for the state side, basically for channel design, the structure design, and it's very fast. And then if you are to use it basically to overestimate your rotor hotspot if you do not consider rotation. And then stator cooling performance, you're looking at insulation class temperature limit on how the materials that you are selecting, how much temperature can they sustain. On the rotor cooling side, you're looking at the magnet temperature limit. And then the rotor effects are necessary if you're going to consider the rotor effects. And then if you go to the centrifugal structural assessment, there as a person, I learned a lot. And the things that you can do beyond the normal yielding of the materials and displacement, you can actually learn a lot from these. So beyond the structure of stresses, what you can actually do is avoiding collisions to check whether your rotor is colliding with your stator virtually. And then the one that is very funny is you can actually, after you land the machine and unload it, can you actually, is it plastic or elastic yielding? So those are some of the things that you can, that is there permanent displacement upon unloading. And then you can check the different types of assembly. So press fitting, bolt preload that establishing contact. And then for what this point says is lamping, rotational, lamped service load and unloading services. So this is the, but we know that in structure, you have to basically create the link between the different borders in transmission of forces. So the housing to housing, for simplicity, we assumed glue connection. And then from the housing to the magnet retainer, so you have the magnet retainer is these ones over there to hold the magnet because of the axial forces. So we are now holding them mechanically with a beaver. We beavered the magnet, then we are holding them mechanically. So we are using contacts and bolt basically. And then housing to rotor yoke, magnet to rotor yoke, and magnet to magnet, anything that has contact with the electromagnetic bodies. So we had two cases. The first cases was contact, we establishing contact using bolts. And the second case, we added glue to that first case of contact. We also added glue, like what you normally do if you're actually assembling it in your own. So the considered design is if you have a press fit, so this piece that is holding the magnet uh, onto the rotor carriers is basically a press fit. What we had was an excessive unseating. So after at high speed, this thing will basically start to come out. And then, so what my colleague did, Mark did, he added both to basically what if now, because it's floating outside, what if you added both over there? And then you see the inner side, there was also unseating, so it will still come out over there, and then you have stresses there at those both locations. Then he said, no, let's bolt it on the, so what we are calling radio on this. So basically to now basically anchor hold it to the contact completely. Then what you have is this excessive stress, and then the same over there. So this is radio, and then it's axial. So we're just gonna show the results for that. So what you see for both preloading, so how much you tighten to establish that contact, you can see that as you increase the bolt preload, the stresses also go up. The goal is to go below that. And then when you look at the axial displacement, because you're looking at the axial is basically the distance between you and the stator, and you want to maintain at least at 1 millimeter at the peak velocity. And that's what Mark was looking at here. And he's looking at for the different levels of preload. What you see is between 0.01 to 0.05, there's a very small difference. But as you go to very high, the more you tighten, you can see the axial displacement actually reduces. So the lead one is towards the inner side. So this is positive Z and this is negative Z. So they are all going towards the stator basically. So then, as I said before, we added glue to this case. We say, let's add glue and see what happens with glue. And this is basically the conclusion. So this is the first case of contact established using bolts. And you can see that this piece, the overhang is going towards the stator, and this is going towards the stator on that side. And the maximum was this is about -4 on this side, which was very high. And then the stresses, you look at the stress distribution, there's very little stress actually on the magnets themselves. And then when you added glue had a very huge implication, nice one at the end of the day, because it also improved the thermal gaps, the thermal conductivity. But what glue did on the, in terms of actual displacement, it actually reduced because now you can see is about 0.1 in the whole, in the distribution. And then the other thing that it does, because now glue is actually adding the stiffness, now they can share the carrying of the loads, of the mechanical loads. The magnetic materials now are sharing with the rest of the carrier. And that's why you see the stresses increasing in the magnet section. So we tell, we know people grew, so continue growing. It helps in terms of damping some axial displacement, but also it's better for thermal conductivity. So for me, that was very important because I realized you can actually look at rotor assembly impact or structural performance actually by simulating without even beyond the normal yielding and axial displacement that we look for. We can check on how does our assembly methods influence how our rotor will perform eventually. So the same can be done on the stator side. Now, because we are short of time, we're gonna go to acoustics. And then I think that's the dessert of the whole thing. And I think this, you find it interesting. So in acoustics, we know the reason why it's very difficult to do axial flux or transverse flux or outer machine, or the inside out machine. It's also very difficult to do acoustics for them. So we know that radio flux in our machine, this is well studied, there's established methods for that. And we see why the difference between the two. The other part, as we said, the axial flux, especially because of the axial, the strong axial force, is very prone to manufacturing asymmetries. And usually you choose the highest point where you have the highest electromagnetic force, which occurs at the peak operating point. That's what we chose before the flux weakening region. And then for NVH accuracy, what you really need to do is consider the energy that you're getting from the different sources and the frequencies. You have to maintain them to ensure that when you're interpreting the results, you are basically mapping the EMAG, in this case, the EMAG forces correctly to the on the other side to be able to see how they interact with the structural modes. So that's the analysis. So the process can be split into two. So the first task is actually trying to find out which kind of harmonics and their shape are coming from the EMAG side, and this you are deriving from the air gap flux density. And then on the acoustic side, you take these EMAG forces and then you map them on the stator mesh. And then after that, we're able to do the full NVH FEM model analysis. With the stator and rotor assemblies, you add the acoustic mesh to be able to do the acoustics analysis. And this way, you're able to do that holistic electromagnetic noise analysis. So why is it different from EVs from ICE? One, we have the motor orders that are coming from the EMAG forces that are twice the electrical frequency of the machine. And then you have the structural modes. And the goal is you don't want the interaction between the two, or you want to be able to control the interaction between the two. Then you have these off-zero harmonics, which are basically the inverter harmonics that are coming because of the switching effect. And you know that normal and ICE engine is going to operate in these low order modes. And then you see the low order mode, they also help you to mask a lot of noise. And then here you are having now this noise that is high-pitched noise that is characteristic of EV machines. So in this case, we are going to consider EMAG forces and structural mode, and because we are using sinusoidal power, sinusoidal currents, we are not using any PWM-driven power electronics. So what you're gonna see is forces and structural modes over there. So the radio flux normal workflow basically, and this is supported by Simcenter 3D. You have your structural FEA model basically, and the same structural model that you use if you are using structural analysis. You're gonna use the same structural model in terms of then in terms of meshing, not the same in terms of meshing. Then you have the EMAG. Usually you extract the forces on the stationary stator, so the stator is not rotating, and then you basically take those loads, you map them, and then you do a frequency analysis on them, and then you're able to extract the orders. And then you try to see are these orders interacting with the structural modes on that side, on the vibroacoustic side, and then you do post-processing and analyzation. So that's the biggest difference between an axial and a radial flux. Is the stator is stationary, and this is where it makes it the process simpler. But in an axial flux or an inside-out machine, it's the rotor that actually radiates the highest amount of energy. But the rotor is also rotating. So on the air gap force side, where we are trying to, as I said before, we have to know which harmonics and wave shapes are coming from the EMAG side, and this is the process. So you're going to go to the air gap and sample the flux density. And then using the Maxwell stress tensor, you're going to transform that flux density to the Maxwell stress tensor. That's what you see. So this is the air gap position, and that's basically the rotor position. So for each time step, you rotate and then sample the air gap and transform it to the air gap stress tensor. Then after that, you do a 2D FFT on that, and then you're going now to be able to extract the spatial orders, mainly contributing to the 10th vibration mechanism. Indeed, because the 10-12 machine, so it's going to be the 10 because you have 10 poles. So this 10 vibration mechanical order. So we can see here we have the positive wave number over there. That is ovalization is that interact with ovalization mode. This is also because the 10-12 machine, you can model the half of it. So that's why the ovalization mode is coming in. Then you have the minus, the negative 4 wave number that is interact with the square mode, the 10 wave number that are with the 10 mode. But also you can see there's a DC mode over there that is going to interact with the axial breathing. So if you have axial breathing mode, this guy is going to be very important, as you see later. So if we use the normal radial flux mapping technique, the one we have today, this is what is going to give you for mapping. So the stator coil maps, them, they are okay. You can see they are rotating in the same way. But if you look on the rotor side, they're actually rotating on the opposite sense. If we use it as, because the code or the normal, if you use the normal radial flux, it does not consider the rotation of the rotor. And you can actually clearly see that. If you look here, you see that the fields are actually rotating in opposite sense, because on the stator side, it's doing the right thing because it's not supposed the rotor is, but on the rotor side, the rotor is moving. So you have to actually collect for that. So for an inside-out machine, axial flux, transverse radial flux machines, you actually have to take into account the rotation. And I think we are the only ones who are doing it today. And then, so what we have done in Simcenter 3D, we have a dedicated rotated mesh mapping that rotates the electromagnetic mesh at each time step, and then it does a conservative mapping. of the forces. And this has been seen to be the best trade-off between mapping, calculation, time, and accuracy. Then you also have to ensure that there's a conservation of energy by having that integral sum of forces. And then the other part that you have to do is you have to check a number of points from the source mesh, the target mesh, and see whether you are mapping in terms of energy and in terms of harmonics. So that's what was done now by now conservative rotating mesh mapping. And then you can see now, not only are they synchronized, so they're all rotating in the clockwise direction, which they're supposed to do, but also the glitch that was there after, because we did only 180 degrees electrical, but you see now it looks continuous for a whole mechanical cycle. So that gives you better performance. So that's the advantage of this rotating mesh mapping. So, and then if you look at here now, this now is more realistic. The roads are more synchronized. So if you look at the rotor, the shading on the rotor side, the shading on the stator side, there's more synchronization in terms of forces. So then, if you look now at conservation of basically the energy and also conservation of the harmonics, then you can see if you use the standard. So the red is a rotating force mapping, the blue is the stationary, the standard. If you the standard, you can see there's no conservation of there's no conservation of the magnitude. So basically, the stationary is the blue. You can see it's overestimating over there some harmonics, and the red basically is the one that considers basically the rotating impact of the rotor. So it's important because you see also when you go to now analyzing the influence of the EMAG on the structural, these orders matters. So then after you finish now transferring the data from the EMAG mesh and you take it you map it on the stationary using the right method that is rotating, then you also need to do your structural model analysis to see which are the most dominant modes or what you're getting from the structure that you have. So based on our structure, as I said before, it will going to have implications because we are holding it. So we assume fixed constraint on the bearing seat. And then we reuse the same basically rotor and structural mode that we got from the structural analysis. And the modes that the most interesting modes that we got were these. So there's mode 1, which is rotating around the bearing seat. But as I said before, there's this axisymmetric breathing mode that you're seeing over there at 575 hertz. Then you have this 69 hertz, the vertical shear mode. And then you have this axial breathing mode, but asymmetric. So here they are moving together. You can see they are symmetric, and here they are moving away from each other. So that will be interesting. And then remember, you also have a DC mode on the EMAG side of things. So now this is the axial flux outer rotor workflow that we're talking about. You have the structural, the EMAG. Now we have a rotating conservative map meshing to transform that to frequency domain, and then you're able to do a more accurate, basically, vibroacoustics analysis. So in terms of setup, you have to include both the stator and rotor effects to rotating conservative mesh matching. And then we can use, at least because of AFM in Simcenter 3D, we can use the structural mesh, and then you add the acoustic mesh. And then there are two things you can do. So you can add the microphones to be able to have if you are seating directivity of the noise, and also the radiated power, so which has to surround. Basically, you have to create a contour or a service that integrates all the energy that is coming from the device, in this case the motor, to find that acoustic power. So the most interesting part is mic 1 is the one that is in front of the machine side wall on this side of the machine, on the side that is not anchored on the fixed side of the machine. Then in terms of analysis, I said before, we look at the acoustic pressure and power radiated at peak load conditions. And then we look at how do these modes interact with electromagnetic loads. So this is the acoustic pressure at mic 1 on the side that is not fixed on a bearing seat. And this is the acoustic power. Acoustic power is basically you are getting all the pressure and integrating it around the whole device to basically quantify, if I have this pressure that coming from the device, how much would it be? Here, this is directivity. You say, if let's assume a device you are told, no, I just want to know what's the noise that I'm hearing, or what's the performance of the noise performance on this direction from a particular direction. So these are basically, you can see, those are the modes. And usually if you look, you'll be like, they are the same, they look the same, but they're not really the same. and those are the EMAG forces. But then if you superimpose the rotor structural modes, then you're able to see that at least here, the difference is very small, but you have this guy over here that is showing up in acoustic power, but you can see there in the mic one, from there, if you're measuring from there, you will not be able to see it. And then the other interesting one is over there, where you see that you have very dominant, very huge energy over there, which over there is very little. Then the next step is basically how can we now analyze? Let's assume now you wanted to be like, how do I analyze these, and how can I now reduce if how can I reduce my my noise or my how can I improve my acoustic performance? So under mode one, and which I found very fascinating with these was, so the red is the total radiated power. Now you're looking at the whole device, and the blue is the individual mode contribution. So individually, you can see it contributes at the top, and then it shades down, and that's why Bart is calling this the not efficient radiator. And then when you go to the second case, which is the breathing mode, where you have also on the EMAG side, you have a very very huge DC component. You can actually see it actually contributes a lot. If you look at the magnitude in terms of contribution, it comes to the overall performance in terms of acoustic power. Then the same thing applies to the third one. It's very close to similar behavior, and you can see that it's not as efficient as a radiator. And then at 270, so these two which have the breathing mode, they contribute a lot, and you can see in terms of magnitude, they actually have a higher contribution. So this has implications if you're an acoustic person, vibroacoustic, and you want to attack the problem on how to improve. Basically, you can see that the ones that you need to deal with are these modes, basically. Those are the ones that you need to deal with, basically, to try to drive down the basically the performance in terms of vibroacoustics. So in summary, we can say that as for acoustics, you need to identify the dominant EMAG harmonics and their shapes, and that's why you're using the air gap force analysis, basically to identify because we are just sampling the air gap, we are not sampling the whole of, especially for an active flux, we're just sampling at the average air gap. Then to identify them, on the structural side, you have to identify the modes. Then you have to map things the right way. And for axial or inside out motors, you need to use the rotating conservative map meshing. And then from there, then you'll be able to analyze the coupling between the two, the EMAG and the structural modes, and see how they influence basically they influence your vibroacoustic performance. So this basically was an example of the first iteration of a multi-domain verification analysis workflow inside Simcenter 3D. We tackled some ways of how can you actually save time in terms of EMAG, how can you play around with your model to help you save time and extract the key performances, characterizing, including demagnetization, loss analysis, and then how can we identify points for CFD thermal analysis, for structural assessment, and acoustic analysis, that's the peak where you have the highest electromagnetic forces. Then for CFD thermal analysis, we actually saw like for stator cooling, you can neglect the rotor effect and get away with it. But then for rotor cooling, because of the strong, especially when you have fanning effects, you really have to consider, so you have to consider the rotating effects. On the structural side, I was actually impressed that you can actually look at the rotor construction, how the rotor is going to be assembled, and the impact that it has in terms of the rotor integrity. And the same can be extended to the stator side of things. Then on the acoustic side, the need for conservative rotating mesh mapping, especially when you're dealing with inside out motors, and to basically to be able to establish the coupling between the EMAG forces and the structural modes. And I think that brings us to the end of the presentation. I know I was lacing. Yeah. I think we have some questions.
Yeah, it seems like we have
like,
some questions in chat. So the first question is from Arvind. Are there any templates available for axial flux motor in Simcenter? If yes, are there any options for coreless axial flux motors?
they are not templates, but you can create your own templates that is it's parameterized basically. And that's what I've done here is I've created a template that is parameterized. I can change the number of ports, the number of slots, Yeah, so you can create your own template that you can drive basically. And that maybe is the beauty of Simcenter 3D because it's cards based. If you have a good, especially if you have a good design team, you can actually design card in that sense. They can actually create an assembly that you can play around with in terms of parameters. So in this case, we can change and we can change our number of poles, number of slots, inner diameter, outer diameter. So that's something that you can do basically, or it can be done for you in terms of services. Yeah.
Gotcha. Thank you. And next question is from Cynthia. Did you happen to study the eddy current loss due to SOMA 700?
Due to
Uh, due to SOMA 700, I'm assuming that's one of the
Sumo 700. I'm trying to find what is Sumo 700.
machines.
Is it the aluminium or what?
Sure. Cynthia, if you want to elaborate that, we can unmute you and
Yeah.
you can ask him directly. So
700. I didn't understand there. Oh, Somalo, yeah, Soma is SMC 700. Yeah. So yeah. So what you have to do is you have to turn on. Yeah, we have turned it on. That's why we have. If you look at our loss analysis, we have some losses associated with the rotor yoke. Yeah, so if you look at the rotor yoke, we have some losses associated with the rotor yoke. But what you have to do is define the bulk conductivity, because the good thing with SMC, because they measure it in bulk, it's not like electric steels. So whatever they give on the data sheet is actually the bulk conductivity for SMC. So you can turn it on, yeah. And that's what we have done over here. On the rotor yoke side, yeah. On the stator core, the same, you have some value for the stator core, yeah.
got it. Okay. I hope that answered the questions. Next question from Arvin again. Is there an option to include eccentricity of rotor during performance study?
uh, an option on the server side or induced by them by the user. So basically what I do is I create my own eccentricity on the model. So when I'm creating the part files, I'll create an ideal condition. Then I'm going to use a command that I can invoke from the solver. So because I have different solutions. And then from that solution, I can say this is my eccentricity axial, this is my eccentricity dynamic, and then I can learn this over. But there's no option that, oh, this is my geometric, make it eccentric. No, you have to create those conditions on the geometry yourself, basically, and then make the rotation reference. Where do you want to rotate against the axis of rotation? Yeah, so it's geometric driven by the user. At this case, yeah.
Sounds good. All right. I think that's all the questions I'm seeing. So just for notes, so this presentation or the recording will be posted on the ATA website later on, so you guys can go find the PowerPoint and the resources. Oh, did I skip one? Yes. Thanks, Scott. So one more question from Arvin. Hi, John. Can you please provide some more information on the 1D ROMs?
Or the PIEs. Yeah, I think I can. Yeah, so what we do is we discovered that in electrical engineering, like the insulation, like how to, you either use an air gap. So like if you have two conductors, you have to separate them with an insulation. So they are insulated. So you have to keep the currents in between one and the other so they don't touch. So we realize what you normally do, you would create a small gap between the two. And then in terms of the measure, you're going to stress the measure because you have to create these small meshes. And then in terms of aspect ratio, they are very small. So basically, you are stressing the measure to create that. So we have, in terms of the magnet solver, it basically has this, what we are calling perfect electrical insulation. Basically, you have the same phase, you apply to that phase, is shared by two bodies, but it just basically restricts the current from flowing from one side to the other side. So that way you can use it for laminating effect. You can use it for what I've done it over there. For this AC winding losses, the same thing that we use for segmenting magnets, for segmenting magnet analysis. Yeah. And it's the same thing that you use for laminating effects, if you want to study laminating effects. Yeah. And then that way now you can turn on eddy currents in that piece. Instead, for these coils, you have eddy current computation, but this one I'm treating them as bulk. So there's no AC losses. It's just this piece that has AC losses. And that way I can be able to quicken the solve for AC loss analysis instead of turning it on for the whole of the model.
All right.
Yeah.
Cool. All right, we'll wrap this up because we're out over the time limit already. So thank you, John, for the presentation, and thank you guys for joining. All right, we'll wrap it up. Thank you.
Thank you.